Hello everyone, my name is Oriel Avraham. I work as a compiler engineer for Mobileye, and in this presentation we're going to talk about instruction cache prefetching, which is an optimization obviously to instruction cache, and it should make your instruction cache much more efficient, much more updated, and it's only going to include the software solution. So if you have instruction cache in your target, this one is for you. So first we're going to talk about the instruction cache, just to put everyone on the same page, to remind everyone what that is. Then we'll talk about the prefetch instruction, and we'll see how we're going to use it to update the instruction cache. Afterwards, I'm going to talk about some LLVM analysis that I found useful during the implementation of this optimization. And at the very end, we'll talk about the performance impact that we managed to get thanks to this optimization. So the instruction cache, just like any other cache, the instruction cache is a small fast memory component inside the CPU. The only difference is that the data that we store in the instruction cache is instructions. And let's take a look at this example to summarize it up. So at the fetch stage, the CPU looks for the next instruction to execute. It has to go to the instruction cache. And if the instruction is there in the instruction cache, we are in a scenario that is called a cache miss. And we can quickly fetch the instruction and move on to the decode stage. But if the next instruction to execute is not in the instruction cache, we have to go all the way back to the DRAM, which is much slower. This is called the cache miss, and only then we update the instruction cache, and we can finally go on to the decode stage. Now, the point of this optimization is to minimize cache misses as much as possible, because while we handle cache misses, the CPU is stalled. It does nothing. It's a big waste of time, and our purpose is to reduce cache misses. So the question that arises is, how do we keep the instruction cache updated? And apparently, in modern CPUs, general purpose CPUs, just like Intel i9 series, for example, we have dedicated hardware that does it for us. It does an amazing job updating the instruction cache ahead of time before the CPU actually needs it. The only problem with this dedicated hardware is that it's expensive. It requires much more power, more space, physical space on the chip, and it's not that easy to implement. So for all of these reasons, usually custom CPUs, like much smaller ones and more dedicated ones, they lack this hardware, they cannot afford it. And what happens is that they don't update the instruction cache at all. They just get a cache miss, and only after they get a cache miss, they handle it and waste a lot of cycles. Now, for us in Mobileye, this was exactly the problem. We couldn't afford this hardware solution, so we looked for a replacement, another solution to add this, to solve this issue. And the solution was inserting this prefetch instruction, adding this prefetch instruction. So what it is all about? So first of all, it is just a hint. It does not change the behavior of the program. And it is a hint to the processor to fetch instructions into the instruction cache. Let's get a little bit into the specifications of these instructions. When it comes to the syntax, it's very simple. Just prefetch with label, just like any jump instruction. When it comes to the semantics, what it does, it signals to fetch the cache line associated with label into the instruction cache. And the last thing what we want from this instruction is we must require that this instruction will be a non-blocking instruction, because we want that once the CPU executes this instruction, it will immediately continue executing the next instruction, and meanwhile, in the background, the instruction cache will get updated. This is the source of the optimization of where we get the performance impact from. So if it's not clear yet, let's take a look at this simple example. I have this code over here, which is divided into cache line n. The first part is associated with the cache line n, and the second part is associated with cache n plus 1. Now, I added a prefetch instruction at the very start of this code, and what happens is once the CPU executes this instruction, take a look, and if you notice that label is associated with cache n plus 1, then cache n plus 1 will get updated in the instruction cache. Meanwhile, we will execute some code, and finally, when we jump to label to cache n plus 1, everything is going to be updated in the cache, and we will not waste any cycles, and we will not get a cache miss. Without this prefetch instruction, there is a high probability that we will get a cache miss and waste a lot of cycles. So this optimization is all about inserting prefetch instructions at strategic location. Keep that in mind. So when it comes to the LLVM analysis that I found useful during the implementation, let's take a look at this case. We have this basic lock, machine basic lock in red, and I already inserted the prefetch instruction to the next cache line, basically just like the previous example. And in this scenario, it should work, but what if this basic lock is part of a loop? Then what's going to happen is that in the first iteration, we are going to update the instruction cache as expected, but from the second iteration and so on, everything is already updated in the instruction cache. So what is going to happen, we are going to waste a lot of cycle running this prefetch instruction without doing anything because everything is already updated. Now, one thing I didn't mention yet is that we want to insert prefetch instructions only when it's beneficial, only when we know it's helpful. Otherwise, we are going to cause something that is called a cache pollution. We are going to evict things that we still need from the cache, replace it with other things. We don't want to do that. So in this scenario, we want to avoid inserting prefetch instruction because it's not always beneficial. And the way to do it is to use machine loop info analysis provided by LLVM. And we can use this analysis to answer the question whether this base lookup is part of a loop or not. And if so, we can decide whether we still want to insert this prefetch instruction. Another case is, let's assume we want to insert a prefetch instruction over here inside the basic block, and we want to prefetch the code from base lookup 2. So it also makes sense, but what if we have this base lookup 3 that also leads to base lookup 2? In this case, it's possible that we first execute base lookup 3, and only then we execute base lookup, and afterwards we execute base lookup 2. And in that case, base lookup 2 will be already in the cache, and when we finally execute base lookup 1 and prefetch label, then it's going to be wasteful because base lookup 2 is already in the cache. So we probably want to avoid such an scenario as well. And the way to do it is to use this machine dominated tree analysis, which basically answers the question whether base lookup 1 dominates base lookup 2 or not. And by dominate, it means that every path of execution that goes to base lookup 2 has to go through base lookup 1. And if that's the case, it's much more safe to insert this prefetch instruction. The last case I want to talk about is what if we have this base lookup 1 that jump to base lookup 2, but in this case, it's a conditional jump, so we are not certain that we are going to actually execute code of base lookup 2 after base lookup 1. In that scenario, it's also not that clear whether we want to insert a prefetch instruction or not, and we can use this machine branch probability info if we have PGO. I'm not going to get into what it is, just because I don't have time, but if we have PGO, you can use this machine probability, branch probability info, and get an estimation of what are the chances to jump from base lookup 1 to base lookup 2. For example, it can tell you that in 95% of the times you jump from base lookup 1 to base lookup 2, and maybe you are satisfied with this number and still want to insert a prefetch instruction in this case. So when it comes to the performance that we managed to get from this optimization, when it comes to the instruction cache performance, we managed to get a 45% reduction in stalls caused by instruction cache misses. And we are not aggressive at all, so the more you're aggressive, you can get the better numbers. But for our workloads, we even got the better numbers, and it mattered the most. And when it comes to the total performance that we managed to get, we got between 3 to 4% of total performance gains in cycles. And it's all up to you, by the way. Basically, the more we suffer from instruction cache misses, the more there is a potential for this optimization, so keep that in mind. And just to summarize what we saw today, we saw that advanced, actually not architectural, advanced CPUs handle instruction cache usually efficiently using hardware components, and simplest ones don't, and we need a solution for that. We saw that we can use LLVM framework to implement such optimization relatively comfortably, and that the compiler-driven prefetching using a software solution is a viable solution that can give you nice results. So just one last thing I wanted to talk about is there's a lot of assumptions that I didn't mention here. If you have any questions, anything that you want to ask, feel free to contact me over here or just after this presentation, and I'll be happy to help. And this is it. Thank you all.